MI's Applied Engineering Laboratory, located in Houston, Texas, conducts drilling engineering research and develops innovative mud testing equipment. MI HDD Mining and Water Well uses this facility to develop new and innovative products for the horizontal directional drilling industry. Since it's difficult for us to visualize what happens in the borehole, we use video to help us understand how the fluids act in the bore and to broaden the HDD industry's knowledge of hole cleaning and cuttings transport in high-angle directional bores. We've developed several specialized flow loops, two of which are shown here, to study cuttings transport in high-angle boreholes. The ERD flow loop has a straight 15-foot-long, 4-inch diameter test section made of cast acrylic. The 1.9-inch diameter drill string, seen lying in front of the ERD loop, can be placed either centered or off-centered and can be rotated up to 150 RPM. The variable geometry flow loop is used to compare different intervals in the same bore. The adaptability of this test section allows configurations simulating most boreholes. The mud pit provides a normal circulating volume of 65 gallons. Flow rates of up to 125 gallons per minute are measured with a mass flow meter. This close-up of our zag tube helps us see the slower, hindered settling typical in vertical intervals. The rapid settling shown here at a 45-degree angle illustrates what is called the boycott effect, with the upward moving clearer fluid layer developing along the upper side of the tube and the downward sliding solids-laden bed slumping along the lower side of the tube. Boycott settling in angled boreholes causes some cuttings to move upward with the flow stream. Others are momentarily suspended, while still others form a bed along the bottom of the hole and slump opposite to the direction of flow. With the drill string lying on the bottom of the hole, water in turbulent flow at 200 feet per minute in a horizontal bore can efficiently clean the hole. With the drill string remaining on the bottom of the hole, the same water in a 45-degree angle borehole cannot clean this interval at the same annular velocity. The net movement of the solids in this case is downward, opposite to the direction of flow. When the pump was stopped, the bed totally collapsed and slid downward. The solids packed off in the tube and completely plugged the annulus. The swirling motion of these solids, seen in slow motion, greatly hinders good hole cleaning and shows us that effective cuttings transport and hole cleaning in one hole interval, the horizontal as seen in the last segment, does not guarantee good transport and hole cleaning in another interval of the same bore. Here we have a bentonite polymer slurry flowing at 200 feet per minute at a 35-degree angle. Notice the rapid solids avalanching when the pump is shut off. This demonstrates the inability of an improperly treated bentonite polymer slurry to suspend cuttings at angles between 30 and 60 degrees. The addition of more polymer to increase the viscosity improved the situation somewhat, allowing less dramatic bed movement seen here in these views from the side and underneath. Hole angles from 30 to 60 degrees are the most difficult sections of the borehole to clean. When the planned borehole includes these angles, the fluids used need to be specifically designed to transport cuttings through these angles. Highly viscous bentonite slurry sweeps are generally ineffective at high angles unless pipe movement and/or turbulent flow simultaneously agitate the cuttings bed. Let's look at this again in slow motion. The viscous slurry readily deforms and passes over the top of the cuttings bed, leaving the bed intact. Dune transport is a typical cuttings transport mechanism. While this results in the movement of a large number of cuttings up the hole, it does not provide efficient hole cleaning. Rotation of the drill string helps break up the dunes, increases the cuttings concentration in the flow stream, and reduces bed thickness. Fluids that provide viscosity at high shear rates but have little low shear rate viscosity, or LSRV, such as this slurry, will erode existing beds as the annular velocity is increased. However, note the inability of this fluid to support even the smallest of these sand particles when the pump is stopped. This type of fluid can be very viscous but still lack the ability to suspend solids. This results in an increase in the thickness of cuttings beds. This sequence compares the cuttings transport capability of a fluid viscosified with a modified pack which has poor low shear rate viscosity on the left, with one with excellent LSRV, a biopolymer, on the right. Note the spiral flow pattern of the solids in the fluid on the right. The ability of fluids with high LSRVs to adequately suspend cuttings is also evident when flow stops. Note the continued slow rotation of the cuttings on the right as compared to the poor support and hopping motion of only a few particles on the left. The drill pipe is 80% off-center and rotating at 150 RPM in both cases. Other additives can be used to produce elevated LSRVs. This Drillplex HDD system, for example, shown at 55 degrees, supports the cuttings quite well when the pump is stopped and quickly resuspends the small bed that formed. Here we see a bentonite slurry lightly treated with a polymer being pumped at 200 feet per minute at an angle of 80 degrees without pipe rotation. This fluid has a low LSRV. Note that even though this fluid is being pumped rapidly, a bed forms because the fluid does not provide adequate solid support. The bed will not slide because the bore angle is close to horizontal. This segment shows the flow profile of a high LSRV fluid in a pipe instead of an annulus. You can see the flat profile of this fluid as the camera moves parallel to the axis of the pipe at the same speed as the fastest moving fluid. This plug zone fills most of the diameter of the pipe, resulting in a low shear rate region in the center of the pipe where the bulk fluid velocity is fastest, and a high shear region adjacent to the pipe walls where the fluid velocity is slowest. Increasing the annular velocity does not greatly affect the flat profile of this fluid. The low shear region in the center is slightly reduced in size, while the high shear region along the walls is somewhat larger. Fluids that have elevated LSRV support capability provide superior hole cleaning at typical annular velocities at high angle as well as intermediate angle intervals, even with a non-rotating drill pipe laying along the low side of the bore. However, note the increasing bed thickness at a 45-degree angle as the flow rate is systematically decreased from 180 feet per minute to 0. Although the fluid continues to provide superior suspension at all flow rates, it is unable to prevent bed formation at the lower flow rates. Note also that no bed slumping occurs until the pump has stopped. This slow bed slump occurs even though the cuttings in the flow stream are very well suspended. As the high LSRV fluid is pumped at 50 feet per minute, the flow profile resulting from the pipe being off-center can clearly be seen here. Without pipe rotation, more cuttings are transported in the 20% off-center annulus on the left than in the 80% off-center annulus on the right. When the pipe is rotated, the addition of rotational energy dramatically improves the cuttings transport capability in the 80% off-center annulus. Rotating an off-center drill string in these high LSRV fluids improves hole cleaning due to the viscous coupling that exists between the rotating pipe and the fluid. A viscous coupling means that as the pipe rotates, the fluid around it rotates with the pipe. The higher the low shear rate viscosity, the easier the fluid will rotate with the pipe, resulting in more of the fluid moving in a spiral that can reach to the borehole walls. This spiral flow breaks up and picks up existing beds and moves the cuttings back into the main flow stream. The key to cuttings transport is transferring the energy in a flowing fluid to the cuttings. Fluids that have high low shear rate viscosities do this much better than those that have low LSRVs. The viscous coupling greatly improves the energy transfer to the cuttings. Remember, the better the transfer of energy to the cuttings, the better the solids transport and hole cleaning. This segment also demonstrates the effectiveness of pipe rotation. Rotation is more effective when the drill string is close to the bottom of the hole and the fluid provides sufficient suspension and a good viscous coupling to carry the solids in a spiral flow pattern. Rotation of the drill string aids cuttings transport even at intermediate angles such as the 55-degree angle seen here. Abrupt hole geometry changes create low-energy areas that allow cuttings to build up. These changes include changes in bore angle as well as hole diameter. The abrupt annular velocity decrease in washed-out intervals allows much more bed to be deposited. Notice the large number of black cuttings swirling around in this washed-out section. Because of this, it's very important that pilot bores be drilled as straight as possible and that proper fluid flow rates are used opposite weak formations. We hope this presentation has given you a better understanding of hole cleaning and cuttings transport in highly deviated bores. Proper fluid technology and additive selection are imperative, since drilling high-angle bores can be much more complex than previously thought. MIHDD Mining and Waterwell sincerely hopes that this knowledge will assist in the successful completion of your next bore.